Hello students, I hope all of you are doing great problems. Today we will do a very interesting problem from ISI-BStat BMath Entrance 2024. This question actually involves a little bit of calculus. You can probably do it in other ways, but I did it using calculus. And it's not very hard, but it shows you a very important principle. How to think about roots of a function using derivatives. How can you describe the roots of a function? Roots means the values of x which makes the function 0. If you replace x by those values, the value of the entire expression becomes 0. Those values of x, they are known as roots of the function. And interestingly, in calculus, you can use derivatives to approximate number of roots. You can actually tell the number of roots. And using this problem, we will learn this technique. So I hope you'll learn a lot from this particular video. And if you are new to this channel, welcome. At Cheenta, we have a small community of learners from 2010. Our students are in some of the best places in the world: ISI-CMI, Oxford, Cambridge, Harvard, MIT. You name it, Cheenta students are there. We have outstanding programs on mathematical sciences. Check the link in the description for more detail. Let's go ahead and try this. So Qnx, a function is given 1 minus x to the power n minus 1 minus x to the power n. When I say it, it sounds same, but you see the expression. It's actually not one function, but a family of functions. Like you replace n. Let's say if I write q1x, then it is 1 minus x to the power 1 minus 1 minus x to the power 1, which is actually 0. Q2x, on the other hand, is 1 minus x square minus 1 minus x whole square. Similarly, you can keep on doing this. Q3x is 1 minus x cube minus 1 minus x whole cube. So this family of functions, how many real roots do they have? Each of them. So the problem says that show that the only real roots are 0 and 1. There are no other real numbers which when plugged in place of x will make the entire expression 0. So I'll write the function one more time here. The family of functions, by the way. So how do you go about it? So here is the main strategy. I'm going to study the points of maxima and minima of the function, and then I will sketch the function. Once I do that using calculus, it will be clear that there are no other roots. First of all, x equal to 0 definitely makes Qnx 0. And x equals to 1 definitely makes Qnx 0. So definitely x equal to 0 and x equals to 1 are two roots. And we want to show there are no other real roots. Okay, so how do we go about it? The first step is we take the derivative of the function. So what is the derivative of this particular function? Well, it is minus n x to the power n minus 1. So I have to use a chain rule here. Minus n 1 minus x to the power n minus 1 times the derivative of 1 minus x, which is minus 1. So what you have is n into 1 minus x to the power n minus 1 minus n into x to the power n minus 1. So there is a very critical point that I want to sort of mention here. the problem, you must assume that n is greater than 1. Because if n is equal to 1, then this is a 0 function. It's always 0 for every value of x. So it has infinitely many real roots. So we are working with n greater than 1. Okay. Now this is the first derivative. You know how to find out maxima. You want to see when the first derivative is 0, right? So the first derivative is 0 means I have to set n into 1 minus x raised to the power n minus 1 minus n x to the power n minus 1. This is equal to 0. I can cancel off the n because n is not 0, or in fact n is not 1, n is greater than 1 as I just described. So 1 minus x raised to the power n minus 1 is equals to x to the power n minus 1. I can divide by x to the power n minus 1 because, and this is a conceptual point, x is not 0. I am assuming that x is not 0 because I already know what's happening at x equal to 0. The function is 0, right? 0 is a root of the function. So I'm only investigating what's happening at x not equal to 0. So you have to be very careful about these things. So once you have this, you can actually divide by x to the power n minus 1 and get this to be 1. Only possible if x is not 0. Okay. So what do we have? We have 1 minus x by x to the power n minus 1 equals to 1. Now you can raise both sides to the power 1 by n minus 1th power. Since we are only interested in real numbers, therefore we have 1 minus x by x is equals to 1, or x equals to 1 minus x, or x is equals to half. So at x is equals to half, we either have a maxima or we have a minima. We might also have an inflection point. We have to check. So to check that, we have to use the second derivative test. So let's take the second derivative. The second derivative of x. What I will do is I can calculate the second derivative from the first derivative. So here is the first derivative, if you remember it. I'll just copy it from here just to have it in front of my eyes. So here is the first derivative, and I want to take the derivative of this. So it is minus n into n minus 1 into 1 minus x to the power n minus 2 minus n into n minus 1 x to the power n minus 2. The only reason this makes sense is because we are assuming n is greater than 1. I talked about this a few moments ago. If n is equals to 1, it has infinitely many roots, so it doesn't make sense to have n equals to 1, right? Okay, so now that's there. So we will plug in this value that we found in the previous step. So at x equals to half, q double prime n x is equals to minus n minus 1 half to the power n minus 2 minus n minus 1 half to the power n minus 2, which is definitely negative. Since the second derivative is negative, therefore we have a maxima. If you don't remember this particular idea, I will give you a short way of thinking about this. Suppose this is a maxima. Maxima means the peak, right? So think about what's happening to the tangent line. The slope of the tangent line is the derivative, right? So this tangent becomes flatter and flatter and completely flat. So it was increasing positive, that is, increasing means if the tangent is like this, then it's increasing. So it's positive. Tangent, slope of the tangent is positive. Slope of the tangent is positive. Slope of the tangent is positive, and now it's 0. Now it becomes negative all of a sudden. So around the maxima, the slope of the tangent was positive, 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 0, negative, negative. So slope of the tangent is decreasing. That means slope of the slope is negative. The second derivative is negative, right? This is how you remember it conceptually. Alright, so maxima is less than 0. That means at x equals to half, there is only one point, x equals to half, where we have a stationary point, where something like maxima minima is happening. So at that point, we have a maxima. So now let's try to draw the graph. So at x equals to 0, there is a root. At x equals to 1, there is a root. At x equals to half, we have a maxima. So the graph must look like this. And it cannot turn back again, because if it turned back again, we would have... So suppose if it turns back again like this, we can show this, actually, that the second derivative double prime x for x greater than half, when x is greater than half, the second derivative is always negative. So it's always decreasing. And before half, it was always increasing. The second derivative is always positive. Because if there was a turn like this, then we would have had another maxima or minima, right? If it has to come back and hit the real line, we would need another minima coming up, which is another stationary point. But we just saw that there is only one stationary point. Therefore, this argument shows, using the idea of derivatives, that it will never go back. It will never make another turn like this. Therefore, there are only two spots where the graph is hitting the x-axis. Therefore, there are only two roots. I hope you learned something from this video. Using calculus to investigate roots is a very old technique. I think it started with Newton. So there are a lot of fun problems around this. You can use the problem books by Marin or Piskunov to actually explore problems like this. If you are interested in outstanding programs in mathematical sciences, you can check the link in the description. We have beautiful programs on Mathematical Olympiads, ISI-CMI Entrances, research projects for school students. I think you'll like them a lot. Alright, I'll see you in the next one. Keep on doing great problems. Bye.